Okay, so thank you coming to this Hiroshima Observatory. I'm Koji Kawabata, I'm director of Hiroshima Astrophysical Science Center. So today, I'd like to introduce our observatory and our research that we are now promoting in these years. Okay, so when did you come to Hiroshima this time? When? This time? 30th of July. Oh, so just a few days in Hiroshima. Okay. Have you taken okonomiyaki?
Yes.
Okay. It's okay.
Very tasty.
Very tasty. Okay.
I like it very much.
Okay. Very good. Okay. So this observatory is not so old, and this is a somewhat a new facility in Hiroshima University. So please hear my talk now. Okay. Okay. So. Oh, sorry. Okay. Yes. Hiroshima Astrophysical Science Center was founded in about 13 years ago, and we have 1.5 meter. The aperture is 1.5 meter. Optical infrared telescope is here, and I will take you to the room later. And the mission of our center is observation of targets of opportunity in collaboration with high-energy astronomical satellite, Fermi gamma ray satellite, and the Hitomi X-ray satellite. And we are trying to reveal high-energy dynamic activity in the universe. And the main target, the main object in the universe is a gamma ray burst. You know gamma ray burst, supernovae, and novae. These are kind of new stars, newly appearing stars, and cataclysmic variables, very actively varying objects, and some these objects we are researching. Okay. Yes, the organization is like this. Hiroshima Astrophysical Science Center is not joined to the Faculty of Science. This is an independent organization, but that we are now tightly collaborating with high-energy astrophysics group in Faculty of Science, and also theoretical astrophysics group is in the Faculty of Science. We are tightly collaborating now. And this center is not so large. Now we have these faculty members, and 4 out of them are permanent staff, and 3 of them others the term is restricted, but some anyway they are very actively researching the universe and astronomy or something. Okay. And also we have many graduate students, in master course, and now we have only 2 doctor course members in this. And these are the target and the themes of their research. Supernovae objects, and also there are some of them promoting instrumentation, making some instruments. They are attached to the telescope and then used for observation. Okay. So why we study our universe? We are here now, and we are trying to find any kinds of scientific hints. And evolution of universe eventually has made us. Any kind of events in the history has related to us. And then the main mission of HASC is to study the dynamics of transient objects, usually very high energy phenomena in the universe, such as these objects, gamma-ray bursts, black holes, neutron stars, or something. So these are questions for you about our universe. How old is our universe? Yes, that's right. It's about 13.8 billion years ago this universe was born. And how large is our universe? How large is our universe? The universe should be much larger than the visible horizon. The visible horizon is 13.8 billion year light year. You know, light year distance scale, light year. But the universe is much larger than this scale. But we cannot know anything beyond this horizon. This is how old is our sun and solar system? Is 4.6 billion years old, about 1/3 of the age of the universe. And how old is our Earth? And when will our solar system end up in? How old Earth is like this. But then how and when will our solar system end up in? Everything has its life and last moment. Maybe if we trust our research in the theoretical research in stellar physics, about 5 billion years later, our sun spends all of its fuel, and its outer layer expands more than Earth's orbit. So they, red giant, like the red giant. Yes. So this is a mission of our center again. So main targets: gamma-ray bursts, supernovae, novae, cataclysmic variable, X-ray binaries, and something. These are the high energy dynamic activity in the universe. So this shows the life of stars. And yes, this is the life of stars. The stars are originally interstellar matter, interstellar gas. And then from them the protostar born. So these gas concentrated by some new force. They concentrate, and then protostar is made, and then they give a light by themselves. So the nucleosynthesis starts in the stellar core, and so they become bright. So this is the birth of star, and then they evolve. And their evolution is different for the low mass stars, like sun, like a solar, like sun. The low mass stars have a very long lifetime, but not so energetic. So high mass star, massive stars have a very short lifetime, and they about 10 million years or 100 million years, they end their life as a supernova. So they explode. But sun have a long lifetime, about 10 billion years or so, and they expel their gas very slowly. But anyway, these gases into the interstellar medium, and then from them new stars born. So this is a cycle of the stellar gas, and also this is a evolution of the matters of some of them making our bodies or something. This is a cycle. And here supernova, black hole, neutron star, and white dwarf. These are the targets, or our main targets. Research with our telescope and some satellite or something. So they are closely connected to these very important objects in the universe. Okay. Recycle, yes. This is a short introduction of a supernova. This is a very important 1987A supernova. This was exploded in 1987. Oh, sorry. So this star exploded, and maybe 10 years later, this supernova shows like this nebula. Now this area is expanding at the rate of 3,000 or 4,000 kilometers per second. So now still energetic one. So in the massive star, also in the sun, the hydrogen is burned into the helium. So the nuclear fusion is occurring in the core of the stellar, like a sun. But in the massive star, eventually the ions and magnesium or silicon, such heavier elements are made within the star core. So in the universe, when 13.8 billion years ago, only we have hydrogen and helium mostly in the universe. But in the star, such heavier elements are made, and then they are cycled, and so now we have many type of heavier elements in the universe, and they made our bodies and also our Earth and rocks, something. So these heavier elements are made within the stars in the universe. So this is so important for this. So this is a kind of mother of our body or something. Sometimes we call star is our mother. Okay, so this is a mechanism of the supernova. So this is the end of the massive star. The end of the massive star, the gravitational collapse of the iron core occurs. Core collapse, we call core collapse. So the massive core supports the outer envelope, but the core is shrunk eventually, within 0.1 seconds or so, they shrunk. So the core collapse occurs. And then they made a neutron star. Neutron star is a very massive and very massive, but very small star, neutron star. And then any gases fallen onto the neutron star, and they are bounce. They bounce, and like this, we have the shock wave occurs, and they go to the outer side, the shock wave. So then this shock wave coming to the stellar surface, then the stellar explodes. Okay. So gravitational collapse of the ion core make shock waves driven by the core bounce and explodes the star. Okay. So our mission, our target, such a not a silent object, but a very active one. So these are the important items that catch up these events quickly, and then follow up the variability in various electromagnetic waves. So we call multi-wave length. So multi-wave length observation for such a transient phenomena is important to study. To study the mechanism and something of such a, because when time takes, so the event is faded, and there is no sign from the star. So we don't miss it, and at the time we should any information from the single event. So multi-wavelength observation is so important.
So can you predict which star will have a nova? Otherwise, for 360 degrees, it's very difficult to which direction you have to catch with the telescope.
Yes. So such a follow-up. So we are doing follow-up observation and finding our surveying such a new stars, other project and other team, or sometimes amateur.
They will give you information.
Yes. Very small but automatical robot telescope are there, and they searching such objects. Yes. Okay. So this is a Kanata telescope. We have this telescope in our dome. Diameter is 1.5 meter, and this telescope was originally constructed by Mitsubishi Electric Company in 1996 for an instrumentation test bench of a Subaru telescope. Subaru telescope is a 8-meter telescope on the top of Mauna Kea in Hawaii. So 8-meter telescope. This is one of the largest telescope in the world, and very actively now it is working. And this telescope was originally constructed for the test bench of this telescope, and then this telescope is coming to Hiroshima here. This is a dome, and we have two instruments, Haupo and O'Neill. These both are made by us and our students. and middle here. One is HALPO is optical wide field polarimeter, polarization, polarimeter and imager and spectrograph. Basically optical instrument, optical light instrument. And O'Neill is optical and infrared simultaneous camera. And one optical band and one near infrared band is inside the one instrument. And the coming light is divided into the optical light and near infrared light. And they are both simultaneously we can measure the light. And spectroscopy and polarimetry are also available here. Yes, this is O'Neill. Is attached on the base of the telescope, and this is O'Neill. O'Neill is here, and the other instrument is here. HALPO is here. So we have two, and more, and just one another small instruments are attached. So we have three instruments in the one Canada telescope. Okay. Okay, this is the last slide of my introduction. So now this is a schematic view of our observation scheme. As I told, we have monitoring the new object. This is a sample of the satellite observation. Satellites have gamma ray satellites and X-ray satellites have a very wide field of view. So they receive a signal from some new stars, and the information coming directly to the Earth, and it is delivered using the internet. So almost simultaneously, we should know the position, not the exact position, but some with an error, some large error, but it is still inside our field of view of our telescope. So we quickly moved to the position and then start the observation. So after the observation, we analyze the images. So sometimes there is some fading object is here, and then we identify this is a new object that was brightened in the X-ray or gamma ray. So now, anyway, we observe the optical light and the infrared light. So there is some optical light and X-ray or gamma ray light. The mechanism of the emission is different. But anyway, they are from the one object or one event. So we can study the objects more precisely or more from many of view. We can see the real nature of the objects, like this observation. Okay. So this is my introduction of our center is finished. That's all. And now I'd like to show our 3D theater. Sometimes we say the 4D theater here, and 3D plus one time direction, time axis. So we say 4D, 4 dimension. Yes. So please take the glasses. And, so now this is a Mitaka software made by NAOJ, National Astronomical Observatory of Japan. This is a free software. But now coming so we use these two PCs and two projectors for left eye and right eye. It is okay. Now you can see the stars and okay. I'm sorry for the. Sorry, but now the software is not good, so we should restart the software. Sorry. Ah, すいません、ちょっとお待ちください。So please wait for a while. Now the software is not coming. Oh, I see. The keyboard is not working. すいません、ちょっとリブートしますね。すいません、ちょっとお待ちください。Okay, the now controller is not working, but now okay. So sorry. So now this is the view of our sky from the Earth, but in the software, the known objects in the universe is inside it, and we can go into the universe, the software. So I will show you the current knowledge of the universe that still our the inside of the event horizon, the horizon. So yes, anyway, I will start this one. So this is now, and we can change to the English one. So yes, this is sky in the north direction tonight, and we can in this system we can change the time like this. Now from Japan like this, the Paris is there, and the stars rotate around the Paris in the north direction, and the western in the western direction, and now the 1 a.m. like these constellations we can see. Yes, like this. Sagittarius is there, things like that there. So around 4 or 5 o'clock, the sun is going up, and now it is noon, like this. So we can go into the. Let's go into the universe here. Okay. Japan and yes, like this we can see the Earth. So this is so we can see the sun, and this is the night side of the Earth. So yes, and in the opposite direction, here we can see the daytime surface of the Earth. So now we start the time of Earth. So the moon is coming here, and here, yes. Now the moon is darkened. You can see. So so August 8th, we have occultation of the moon. We can see in the very early morning, in August 8th, and then now we start, and then a moon coming this here, and so this month we in the this month the moon, sun and moon and earth align in one line like this. So we can see here, like here. So at that time, so this is shades of the moon go across the North America, and in the some places in the North America on this day they can see the total eclipse of the sun this month. Yes, but yes, so such like this, Earth and Moon moves like this. But this is a very near side of the Earth still. So we go far and far, and now we can see the solar system like this. Very fast. So the Mercury is most nearest planet in the solar system from the Sun. The Mercury and Venus and Earth and Mars rotates like this. And also there are many asteroids, small bodies of the solar system rotates like this. All the objects rotates this way, in the same way. But, yes, like this. Oh, sorry, something is like this. And there is a Jupiter and Saturn that's there. In this scale, any object, any planet like a point. So now we enlarge each object to see the surface of each planet. Yes, like this. The Mercury and Venus. Venus and Earth is nearly the same size. And here the Mars rotates. Mars is a red one, red planet, and smaller than the Earth. Yes. And Jupiter is the largest planet in the solar system, and Saturn has rings like this. And Uranus and Neptune and Pluto are there. And around there, now we have we see the many large objects like Pluto are there. But only the planets up to the Neptune rotates in the same plane. So the Jupiter and the Earth, any of planets rotate around the Sun in the same plane. But Pluto and other objects rotates not the same plane. So these stars, these Pluto on the Haumea and Makemake are not the origin is different from the planet. So because the orbits are not the same. And yes. So now we know that there are many such large trans-Neptunian objects, and Pluto is a prototype of the prototype, and this was also counted as a planet, but now it is outside of a planet, and these are called as trans-Neptunian objects like this. Okay. Okay. So this is nearly the edge of the solar system, but the universe is more wide. So now go far and far. And this is a 1 light year distance, 3 light year, and 4 light years. There is Alpha Centauri. Sirius, Arcturus, and Vega are the stars of the neighboring stars of the Sun. And far and far, there are many stars, and go far and far. And then we know that the Sun is only one star of our galaxy, Milky Way galaxy. So Milky Way galaxy has 100 billion stars. About 100 billion stars are there. And solar Sun is just one of them. And is not the center of the galaxy, but somewhat rural area of the galaxy. Okay. This galaxy is go far and far, and this scale, 1 million light-year scale. So any point is a galaxy, and go far and far. This 1 billion light-year scale. There are many points like this, and this is like a butterfly, but this is only the known galaxies are there. Each point is a galaxy, known galaxy. The direction and distance is known. So this black area, in the area, the observation have not been done, this area. Or we cannot see them because our galaxy have many dark clouds, and we cannot see beyond the dark clouds. So that we cannot know them. Okay. So here. So this is horizon, event horizon of our universe from the sun or from the Earth, 13.8 billion light year there. Okay. So and any point the quasars are kind of proto galaxies, blue points, and white points are the normal galaxies. So we know many of them. And from these, the distribution of the galaxies is not uniform. Rather, there is some voids, no galaxies, but some fair the galaxies are very clustering. So these non-uniformity is also information of the origin of our universe. So the ages of the universe is calculated from these information. So this is some inhomogeneity that the universe originally have at the Big Bang. So, okay. So let's return to the Earth now, and then end of this talk. So this is a world of the galaxies. There are many galaxies there, and now we are going to our Milky Way galaxy and to the sun. Here, the sun is here, and these are the neighboring stars of the sun, and then going into the solar system. Oh, something's wrong. Now you can see it? Oh, sorry, something is wrong. Okay. Sorry. Anyway, so this is a now known universe is there. This all the data from the observations. So sometimes we study in the calculation or the in the theory we study the universe. But these are all the known universe. So how is them? Okay. So let's go to into the dome, our dome, and we show I will show the telescope, kind of telescope.